do this material. All right, if we start with x cubed minus 125 over x squared minus 25, can I factor either one of those? In other words, that's the key to doing each one of these problems, is being able to factor the numerator and the denominator.
So x minus 5 and then x plus 5 for the bottom.
Right. How's the difference of cubes? Notice that the top is the difference of perfect cubes. So what does a cubed minus b cubed factor into?
X minus 24.
Let's do it in terms of a and b, and then we can use that information for every other thing.
Okay.
So what is it in terms of a and b?
So that'd be a squared?
No. Here's a good way to memorize. Let me go through it all. At the top, I've got difference of perfect squares, right? Not in the top, but right here. Well, the first term is always linear, and it always matches the sign of what you started with. The second term is what?
Isn't that a trinomial?
Well, a squared minus b squared is equal to a minus b times...
Oh, okay. For the squared, not the cubed.
Right. Okay. However, there's a connection between all three of them that I want to show you that'll help you memorize what it is. Okay. Difference of perfect cubes also starts out with a linear term. Linear meaning nothing is being squared. With the same sign as I started with. And then the second term is a squared plus opposite sign, ab plus b squared. And then finally we have the sum of perfect cubes. And the first term is linear with the same sign as I started with. And the second term is just like this one with the opposite sign. In other words, the middle term is going to have the opposite sign of that. So it's going to be minus ab plus b squared. Notice how similar these two terms are. In fact, notice how similar the difference of perfect cubes and the sum of perfect cubes is. There is no sum of perfect squares. In fact, when it's even, you never have a sum. There's no sum of perfect fourths either. But there is a difference of perfect fourths. But they don't give you that expecting you to memorize it. These three you need to memorize. The easy thing about these is every one of them starts with a linear term with the same sign as what you started with. Well, you already know the difference of squares. So the only thing you really have to memorize is what that term does, because you know for the sum of cubes it does, everything's the same except the sign on the middle term. Okay? So it's actually, even though it looks very complicated, it's actually fairly easy to memorize these three. And you need to memorize those three to do problems like this. Because what we have in the numerator is the difference of perfect cubes. What is A and what is B?
X and 5.
Okay, so what's the first term?
So x minus 5.
Second term?
X squared plus 5x. And then plus x squared.
Plus 25 squared.
25, sorry.
That's okay. Or, excuse me, plus 25. In other words, that last term is b squared. B is 5, so it's 25. Okay, and then factor the bottom, which is difference of perfect squares.
So x minus 5 and then x plus 5.
All right, so that's the first step. So notice we can cancel the numerator x minus 5 with the denominator.
Mm-hmm.
And when I say cancel, it's not like it makes it disappear because there is still a restriction on our domain.
Right.
We still cannot, it produces a hole.
Yes.
Okay, instead of a vertical asymptote. In other words, wherever the denominator is equal to 0, you generally have vertical asymptotes.
Okay.
Unless one of the factors has been canceled out, and then you don't have a vertical asymptote at x equal 5, you have a hole.
Okay.
So you would graph that remaining function.
Okay.
And you would say not only can x not be equal to minus 5, in other words, that would give you a vertical asymptote, but it also cannot be equal to plus 5. So as far as the piecewise function goes, well, the two things I can start with is that x cannot be equal to minus 5. There's a vertical asymptote there.
Right.
And x cannot be equal to plus 5, there's a hole there. So there's my vertical asymptote, there's a hole.
Okay.
So the piecewise function that I end up with is going to have a vertical asymptote at negative 5.
Mm-hmm.
It's going to have a hole at plus 5. Wherever the curve is, there's going to be a hole right there. The hole isn't going to be on the x-axis.
Okay.
I don't know where the curve is. I'm going to have to do further thinking about this.
Okay.
But in terms of defining the function, it would be, let's see if I can write it out. Not sure what her 4 steps are, but they should look something like this. When x is less than minus 5, the function is x squared plus 5x plus 25 over x plus 5.
Okay.
In other words, this function right here, whenever x is less than minus 5.
Mm-hmm.
In other words, if I'm looking at my picture, I'm talking about this range right there. There's no restrictions in that entire range. X can be anything up to minus 5.
Okay.
Well, at 5, it doesn't really exist. There's a hole there. It's not defined for x, at minus 5. Hold on a second. My hole is at 5. Okay. So now we have the region where x is greater than minus 5 and less than 5.
Mm-hmm.
Let me put a little room in there. And it's the same function.
Right.
X squared plus 5x plus 25 all over x plus 5. You don't see many piecewise functions that end up being the same function everywhere in each part of the piece.
Right.
So this threw me off a little bit because of that. You don't generally do this step. In other words, what you generally do is reduce that and say where your vertical asymptotes are and where your holes are, and maybe where an oblique asymptote is, but you don't generally write it as a piecewise function. But I guess I can. The only other place would be x greater than 5. And then it's the same function again. In other words, it's the same function in all 3 spots. The only advantage in writing it as a piecewise function is that you get to eliminate -5 from your domain and 5 from your domain.
Okay.
Okay. She says show the 4 steps outlined in class. The 4 steps, I can't imagine it's any different than the way I did it, but I can't count to 4 unless factoring the top is the first step, factoring the bottom is the second step, canceling the common factors is the third step.
Yeah.
Finding your domain is the 4th step.
Yeah.
Perhaps.
I think that's it. It's she has it. She gives us on the sample problems like x equals something before the actual equation, so it'll be like x equals 0 or x equals 4, and then you have to, here, I'll try and send you a picture of it.
Okay.
Yeah.
It's not one of these other pictures that you sent me? Because you sent me 3.
No.
Okay. Yeah, it's a little unusual. I mean, I've done a lot of tutoring on limits, and I've never, ever been requested to show the piecewise function.
Yeah, okay, I just sent it to you.
All right. Internet must be slow today. Tell you what, that meeting was a little intense.
Oh, yeah, thank you for helping.
why I'm a tutor and not a teacher.
Yeah, she's something else.
She is something else. She's not sure what exactly it is, but I wouldn't want to judge her.
Yeah.
Still haven't got it. You sent it to the same email address as you sent the 6 attachments?
Mm-hmm.
Oh, there it is.
Perfect.
So
those are the sample problems. But with the ones that she gave us, it doesn't have like an x equals.
okay. So here's it looks like the review of factors in the denominator.
Yeah.
Okay. This was difference of cubes divided by difference of squares. She did exactly the same thing I did on our problem.
Yeah.
And that means, that's what that arrow means, that implies that you have a hole at 2, oh yeah, the one that factors out.
Yeah.
Vertical asymptote at x equal -2. So that's the perfect curve for that example.
Right.
Now, how would you describe that as a piecewise function? Exactly as we did. From
Okay.
minus infinity to minus 2, it would be this function. X squared
Okay.
plus 2x plus 4 over x plus 2.
Mhm.
And then it's not defined at minus 2, but from x going from minus 2 to plus 2, same function.
Mhm.
And the third part of the piecewise function is when x is greater than 2, same function.
Mhm.
So there's two missing parts in the domain of the piecewise. In other words, the upper right-hand part that you always fill out, this part here, let me draw it. On my picture here, this is what I call the domain of a piecewise function.
Okay.
And usually that's where I like to start. I like to start right there whenever I'm graphing or thinking about a piecewise function. I'm going to start from negative infinity and I'm going to go to minus 5.
Okay.
In that area, I'm going to graph this function, or
Okay.
this thing over x plus 2. And notice that does not simplify anymore. It never does. Whenever you start with difference of cubes over difference of squares, you never end up with a quadratic that can be factored.
Okay.
Okay? So there's no point in even trying to figure out, does that factor into, x plus 4 times x plus 1 or anything. And it doesn't.
Okay.
It doesn't. In order to figure out what this graph would look like, you'd basically have to plug this into your calculator. Either the original or x squared plus 2x plus 4 over x plus 2.
Okay.
If you plug in either one into your calculator, you'll get a graph that looks something like this. The only thing you won't get is that hole, because the calculator doesn't know it knows that hole is there, but it's so infinitesimally small that it can't really draw it. In other words, that hole exists only at x equal 2.
Okay.
Nowhere else. And x equal 2 is one point in an infinite number of points, even between, 1.5 and 2.5.
Okay.
It's a single point out of an infinite number of points, so it's not very wide. And so the hole typically does not show up when you put these kind of things into a calculator.
Okay.
The only reason we know it's there is because we solved it algebraically, and
Yeah.
we know that that domain restriction does not disappear just because we cancel that factor with that factor.
Okay.
Okay?
Mhm.
So this problem here was done exactly as I did mine, or as we did the very first one. She doesn't have any examples that end up listing it as a piecewise. Maybe she does. C looks like it does that.
Yeah. And then at the end of
She's
B.
done it a little different. In other words, she didn't do it the way I did it. She didn't go from negative infinity to 3.
Yeah, she describes it as you're trying to like plug the hole, basically.
Oh. Well, I'm not sure I agree with her on that. Seriously. No, x does not exist at 3. It's a hole. There's no,
Right.
in this example down here, x does not exist at 2. The x doesn't exist and the y value doesn't exist. So to say that y is equal to 5/6 when x is equal to 3, x cannot be equal to 3. Ah, I see what they're saying. That would be the limit.
Yeah, she
Limit
says you're
of the
trying.
function would be
Yeah.
5/6 as x approaches 3. In other words,
Mm-hmm.
looking at this one down here, we can see that as x approaches 2, the limit is going to be 3.
Okay.
So the limit exists, but expressing it as a piecewise function, I don't think that's mathematically correct. It's
Okay.
not equal to 5/6 when x is equal to 3. X cannot be equal to 3.
Okay.
It would be okay to say the limit is equal to 5/6 as x is equal to 3. And since this is a discussion on limits, I can kind of see where she would want to say that. But that's all you can say, is that the limit of y would equal 5/6 as x approaches 3.
Okay.
You can't really say that it's the value is equal to 5/6.
Okay.
All right. But this does kind of show how she wants you to give your answers in this other part here.
Yeah.
Let's see. How do I go back? Let me go back this way. Did I get another email from you?
No.
All right. We don't have much time, but we might have time to do number 2 here. Figuring out how to write them in piecewise is not the important part. The important part is figuring out what the resultant function is and what your domain restrictions are. And if she wants to figure out the limit, that's fine. But this one. Can you factor the numerator?
You could pull out an x squared and then we'll split it into 2. No?
No, the numerator is a cubic. There is no greatest common factor that I can pull out, and I can't group it. In other words, the only way I can even attempt to factor the numerator is by using the rational factor theorem, where the numerator has to be a factor of 30 and the denominator has to be a factor of 1. Well, I can certainly factor the denominator. What's the denominator factor into?
X minus 3 and x plus 3.
So what would you suspect one of the factors of the numerator might be?
Either x minus 3 or plus 3.
How are we going to figure out which? Let's synthetically divide it.
Okay.
Okay, here's synthetic division, and I'm only going to test 2 values. I'm not going to test all rational factors of that. I'm going to test plus 3 and I'm going to test minus 3 because I highly suspect one of those is a factor of the numerator.
Okay.
So let's just try it. How am I going to tell if 3 is a factor, if it's a 0?
If you get 0 at the end.
Okay. So you remember how to do this synthetically? Help me out here.
Do you just start with 3? Or do you start with 1?
Bring the 1 all the way down. That's your start.
Okay.
Then you
and then
start
multiply.
multiplying and adding.
Yeah.
Now I add that, that's minus 1. Multiply, that's minus 3. Add, that's minus 14. That's minus 42. That's not a factor.
Okay.
Let's try minus 3. If it's not a factor, I don't care about it. It's not going to be part of the problem. But I bet anything minus 3 is a factor.
Okay.
Bring down the 1, minus 3, add, multiply, add, multiply, bingo.
Okay.
So what is the linear factor of the numerator? In other words, I now have between that and this, I know what the numerator factors into. What does it factor into? What's the linear factor and what's the remaining quadratic factor?
So x minus 3 would cancel?
No, it's actually x plus 3
Would
because
cancel?
the number, well, yeah, but not yet.
Okay.
We're still just trying to factor the numerator.
Mm-hmm.
The fact that minus 3 was one of the zeros means x plus 3 is the linear factor.
Okay.
Remember, it's always the opposite sign.
Okay.
Okay? In other words, if you are solving an equation and you come down to x minus 4 times x plus 2 equals 0, well, then the zeros, I set that equal to 0, that equal to 0, so my zeros are that and this. This is the number I stick in the box when I'm doing synthetic division.
Okay.
I don't stick that in the box. That is the linear factor, that is the 0.
Okay.
Okay? So,
Yeah.
I know that x plus 3 is the linear factor. What's the quadratic? And I can do my synthetic division. This is the quadratic.
Oh, okay.
What is it?
So that would be x
Squared.
squared minus 7x. And then plus 10.
If I were to multiply that times that, I will get that original numerator.
Okay.
And I know that because I divided the original numerator by x plus 3. That's what that was all about. And I got a 0 remainder, which tells me that that is a factor.
Okay.
Okay? Now, that's my numerator factored. Well, my denominator factored, I know it was x minus 3 times x plus 3.
Mm-hmm.
That's what gave me a clue as to how to factor the numerator. Well, that cancels with that, and what I have left is my answer. Notice that does factor. The quadratic factors to x minus 5 times x minus 2. Not that that helps because neither of those will cancel out with this x minus 3.
Right.
It is an interesting observation, especially after I told you that it never, well, difference of perfect cubes does not ever produce a quadratic that factors. But you can certainly have a polynomial that might factor, like this one does. But the answer is going to be this quadratic over this linear term, where x cannot be equal to 3. And what she's going to do is when x is equal to minus 3, she's just going to substitute it in here and say that y is equal to that number when x is equal to minus 3.
Okay.
And I absolutely think she's mistaken. You can't really say y is equal to that. You can't say g of x is equal to that. What you can say is that the limit of g of x would approach that number as x approaches minus 3. But that's all you could say. There's no g of x equal to that when x is equal to minus 3.
Okay.
X can't be equal to minus 3. That's part of the domain restrictions. That's why there's a hole there.
Okay. But so for her purposes, you would just substitute negative 3 in.
Right. She doesn't do when x is equal to 3 because she knows that that's a vertical asymptote. There's no way x is ever equal to 3. But there's no way x is equal to ever minus 3 either.
Okay.
But the way she does it, that's the way you do it. In other words, when you get down to your final answer, which is this.
Right.
That's everywhere except x equal 3. And then for x equal minus 3, go ahead and substitute minus 3 in there, minus 3 down there, and come up with a number.
Okay.
He's going to say that's what y is equal to when x is equal to minus 3.
Okay.
You're basically going to use that procedure everywhere here.
Okay.
Notice that that's a tough cubic to factor.
Yeah.
Our only way we did it was that we could guess at one of them.
Right.
Number 3, that's just sum of squares, sum of perfect cubes.
Okay.
This factors, one of these factors will cancel out with that linear factor. And on the bottom, use a similar strategy that we used on number 2 for number 4. You're going to have a hard time factoring the numerator. But know that one of the factors is going to be either x minus 1 or x plus 1, almost certainly. Because that's what the denominator factors into. Okay? Emma, you still there? Somehow we got disconnected, but I got to go anyway. I got another session. I will talk to you next time.